Good morning to all of you. I'm Dr. Nitu Gallo. I am working as an assistant professor in St. Andrews Institute of Technology and Management, Gurgaon. I am from the Applied Science department, and my subject is chemistry. And this is my 26th lecture, and it is a part of the our fourth unit, that is the spectroscopy and its technique. So here the topic which is covered in this lecture, that is the NMR spectroscopy. Here, the topic, that is the nuclear magnetic resonance, or it is called the NMR spectroscopy. So it is related to the topic, that is the spectroscopy and its technique. And in our previous lecture, we have discussed that the general basic introduction of the spectroscopy. And in this series, we have already discussed about the ultraviolet spectroscopy and the infrared spectroscopy also. And now the third type of the spectroscopy, that is called the NMR spectroscopy. And the NMR spectroscopy stands for, that is a nuclear magnetic resonance. So here, firstly, we go with the introduction of the NMR. So there is the nuclear magnetic resonance. It is a spectroscopic technique which is based on the absorption of electromagnetic radiation in the radio frequency region. And this region is the 4 to 900 megahertz by nuclei of the atom. Okay, here one thing is important, that firstly we know that the NMR stands for the nuclear magnetic resonance. And what is the information by the NMR spectroscopy? NMR स्पेक्ट्रोस्कोपी हमें कौन सी इंफॉर्मेशन देता है? तो NMR spectroscopy, it gives the information about the proton. And here it gives by the help of NMR spectroscopy, we can find that the how many number of protons are present, those are magnetically distinct. Okay, or other simple language, we can say that it gives information that the number of protons which have different chemically environment. We can say same that is the same meaning of the information of NMR. So here we can say that by the NMR spectroscopy, we know about the information of the protons and the number of protons which have the different chemically environment. So here the proton nuclear magnetic, it is also called the proton nuclear magnetic resonance spectroscopy. That is one of the most powerful tools for elucidating the number of hydrogen or proton in the compound. Okay, so uh, we can say that the nuclear magnetic resonance, it involves the interaction between oscillating electromagnetic radiation and the magnetic properties of certain magnetic nuclei, notable the nucleus of hydrogen atom, the proton. So here are some examples. Isotopes, magnetic isotopes are the 13 carbon, 1 hydrogen, 19 fluorine, 14 nitrogen, 17 oxygen, 31 phosphorus, and so other. So if the nucleus is not magnetic, okay, so it can't be studied by the nuclear magnetic resonance spectroscope. Okay, here in the we know that as the electron can spin, same here the nucleus also can spin. Okay, so here we can check that the nuclear spin quantum number, that is denoted by the I, and we can say that if the I is zero, I is equal to zero, it means the nuclei is spin inactive, or we can say that that is NMR inactive. And if the value of I is not zero equal to zero, so the nuclei is spin active, or we can say that is the NMR active. Okay, so here it is used to the study of the wide variety of the nuclei. These are the example. And here Now then, come to the next topic, that is the nuclear spin. When we talk about the nuclear spin, so as we discussed that the nuclear can spin just like the electron. So that the just we can say that the just as the electron spin about their axis, it is believed that the proton and neutron, which is present in the nuclei of atom, so they can also spin about their axis. Like electron, proton and neutron is assigned a spin content number is equal to 1 by 2. Okay. So here the suppose the spin quantum number for the nucleus can have can then have the value 0, half, 1, 2, etc. But depending upon the number of neutrons and the protons having the parallel or the anti-parallel spin. Okay. So here we can say that we can just as the electron, the nuclei can also spin. Okay, so like the electron, each proton and the neutron is assigned a spin quantum number that is equal to one half. And here the spin quantum number is noted by I, and it is related to the atomic number and the mass number of the nucleus. Here we can see that for the nuclei in which the sum of proton and the neutron is even, as well as the number of each of them is also even. So that is the mass number as well as the atomic number is even. So I value of I is 0. We know that when the I is 0, that means the nucleus is spin inactive, or we can say that is the NMR inactive. Okay, and then the other for second part, that is the for the nuclei in which the sum of protons and the neutrons is even, but the number of proton is odd. It means the mass number is even, but the atomic number is odd. So the value of I is equal to 1, 2, 3, etc. Okay. So here the nuclear spin is integral. Okay. Next, then when we talk about the other nuclei in which the sum of protons and neutron is odd, it means the mass number is odd. So I is always odd, integral multiple of 1 by 2. Here the small chart by which we can explain the again explain this important thing, that the half integral, that is if the atomic mass is odd, atomic number is odd, and it means it is the NMR inactive. Then when the atomic mass is odd, atomic number is also is even, so that it is again NMR inactive, it means the spin inactive. And when the atomic mass is even, atomic number is odd, it is again NMR inactive. And when the atomic mass is even and atomic number is also even, okay, so that there are this is called NMR inactive. And in the three cases, so we can see that the three cases where the atomic mass or atomic number or there are that is the, it means that here the value of I is not 0, so that it is the NMR active. And atomic mass or atomic number even, it is NMR inactive, sorry, NMR active. And atomic mass even, atomic number odd, so we can say there the value of I is not 0, so that spin active or NMR active. And when the both are in the even, so that here I value of I is 0, so that there are spin inactive, or we can say that is NMR inactive. Okay, so here the element with either odd mass or odd atomic number have the property of a nuclear spin. Okay, so since a nucleus possesses an electric charge, the spinning nucleus give rise to a magnetic field. So whose axis coincide with the axis of spin, thus each nucleus can be considered as a tiny magnet. Here this is the important point. there, and when the nucleus is considered as a tiny magnet, when because nucleus is it is very small and it has the proton and neutrons is here, and we know that the electron rotate around the nucleus. So when we applied the uh, electric field or the magnetic field, extramagnetic field, so that it work as a tiny magnet. Okay, so having a magnetic moment, so that each nucleus with the I is not zero, so has a magnetic moment. However, when the nuclear with I is zero, do not possess this magnetic moment. So that's they are non-magnetic, hence they do not absorb in NMR. If the external magnetic field is applied, the number of possible orientation calculated. Okay, or we can say these are the number of allowed spin. Okay, for if we take the example of hydrogen here, so here the spin number I is equal to 1 by 2 for hydrogen, and there are the possible orientation or allowed spin. These are the 2i plus 1. Okay, then when we put the value of I, that is half, so 2 multiply with half plus 1, it gives us 2. So that there are the two allowed spins are possible. Okay, and they may be, for in the case of hydrogen, they may be the plus half and the minus half. Okay, so now there is the we can explain here. Yes, here that is the this energy I is half, and in that when the I is half in the case of hydrogen, so means there are two allowed spin are possible, or there are the possible orientation is 2. So these two possible orientation are plus half or minus half. Okay, so this I that the here is the energy, and the field strength is B0. That is when we applied the magnetic field. So here the I is split, and when it is split, so then the plus half and there is the minus half. So it has the lower energy because it align in the direction of the magnetic field, and this is goes to the direction of the opposite of the magnetic field. So it has the minus half. Okay, so we can say that in the absence of electrical magnetic field, so in the absence of that is the extra magnetic field. In the absence of the external magnetic field, all spin splits of the nuclei, they have the equal energy. भाई जब तक हमने कोई मैग्नेटिक फील्ड अप्लाई नहीं किया है, तो इट मीन्स जितने भी न्यूक्लियाई हैं उनकी सबकी एनर्जी इक्वल होगी. ओके, और जब हम मैग्नेटिक फील्ड अप्लाई करेंगे, तो जो मैग्नेटिक फील्ड के डायरेक्शन में अलाइन करते हैं, they have the lower energy, and other those have the higher energy which oppose the magnetic field. हाँ, मैग्नेटिक फील्ड, इट मीन्स उनको ज्यादा एनर्जी की रिक्वायरमेंट होगी. ठीक है, so this is here it is the diagram. Before going to the principle of the NMR, here I repeat the information about the NMR spectroscopy. Here we know that the NMR spectroscopy involves the interaction between oscillating electromagnetic radiation and the magnetic properties of certain magnetic nuclei, like the proton of the hydrogen atom. So it is also called the proton NMR spectroscopy. Okay, and the NMR absorption of the radio wave in the presence of magnetic field is accompanied by the nuclear transition, and that is why it is known as the nuclear magnetic resonance. Now, here are the now we talk about the spin quantum number, and the spin quantum number for the nucleus, they counter values the 0, half, 1, 1.5, 2, etc. So these are depending upon the number of neutrons and the protons. Okay, so they having the parallel or the anti-parallel spins. And when the We know now we know about when the sum of the protons and the neutrons is even, the mass number and the atomic number is also even. So then the nuclear spin is 0. And for the nuclei in which the sum of protons and the neutrons is even, but the number of proton is odd. So the mass number is even and the atomic number is odd. So the nuclear is then nuclear spin is the integral. And for nuclei in which sum of proton and neutron is odd, so then nuclear spin is always odd, and it has an integral multiple of 1/2. Okay. Now come to the we are going with the principle of NMR. So here we can say that is the uh, tiny magnet, or that is we can say it is a nucleus which can spin. This is the spinning nucleus. So it can there is a um, rotation, or they can be they can spin uh, uh, at its axis, but here we see that it is tilt from its axis. So according to the NMR principle, now we discuss that point. So the theory behind NMR the, comes from the spin of the nucleus, and it generates a magnetic field. Without an external applied magnetic field, the nuclear spin are random in direction. Okay, so here we want to say that the imagine a nucleus that is of spin 1/2 in the magnetic field, है ना. तो और वन थिंग इज इम्पोर्टेंट कि जब तक हम कोई एक्सटर्नल मैग्नेटिक फील्ड अप्लाई नहीं करेंगे, तो इट मीन्स कि जो स्पिन है, स्पिन ईच स्पिन स्टेट have the same energy or equal energy, and when we applied the magnetic field, so there is the splitting between the energy level. So this nucleus is in the lower energy level, which one? That is the magnetic moment does not oppose the magnetic field, क्योंकि वो सीधा उसी की डायरेक्शन में चलना शुरू हो गया. So it means it does not oppose, and so it has the lower energy level. The nucleus has been on its axis in the presence of magnetic field. The axis of rotation will process around the magnetic field. ठीक है. सो द हेयर एक सीधे से है कि जब भी हम मैग्नेटिक फील्ड अप्लाई कर रहे हैं, तो हमारी मैग्नेट जो है वो एक टाइनी मैग्नेट की तरह से काम करेगी, छोटा मैग्नेट बन जाएगा. तो इस कंडीशन में it oscillates. Here is the frequency, of precision. Okay, that is a that is called the precisional frequency, or it is also called the Nmr frequency. So which is identical to the transition frequency, है ना. So here we can see that there is the applied magnetic field applied कर रहे हैं हम लोग. So we can see here that is a precessional orbit, and here is a magnetic field applied, and this is the spinning nucleus here. So हमने अब अगर हम एक एग्जांपल लेते हैं, सपोज हमारी जब अर्थ है, हमारी अर्थ एक मैग्नेट है, और जब ये रोटेट करी तो ये भी अपने एक्स से थोड़ा सा ऑलमोस्ट 23.5 डिग्री एंगल टिल्ट होके घूमती है ना. सो दैट इज here is a difference between the x axis and its the tilt precisional frequency we can say. So it is also called the precisional value. So here the it oscillates same the frequency, and जब अप्लाई करेंगे तो इलेक्ट्रिक फील्ड और मैग्नेटिक फील्ड हम लोग अप्लाई करेंगे, बट इट आल्सो अप्लाइड अ इलेक्ट्रिक फील्ड हियर. सो हियर वी कैन से दैट दिस वन, the nuclear spin is random in the direction, but when an external magnetic field that is denoted by the B0 is present, the nuclei align themselves either with or against the field of the external magnet. Clear? So if the external magnetic field is applied, an energy transfer, that is delta E, is possible between ground state to excited state, as we know. So when the spin return to its ground state level, the absorbed radio frequency energy is emitted at the same frequency level. Okay, so the emitted radio frequency signal that gives the NMR spectrum. भाई जब उसको एनर्जी मिल गई तो वो उसमें जब ग्राउंड स्टेट से वो एक्साइटेड स्टेट में चला गया, एंड जब व्हेन द स्पिन रिटर्न्स इनटू इट्स ग्राउंड लेवल, तो then the absorption radio frequency energy is emitted. Okay, so here the emitted frequency radio frequency signal that give the NMR spectrum of the concerned nucleus. हम हमें वही चीज देखनी है. So the emitted radio frequency is directly proportional to the strength of applied field. So here we can see there is the, if the nuclei one and it shows a plus half and the minus half, we can also denote it, the plus half is the sigma alpha and the minus half is the beta. And here this is the B naught is the extra magnetic field. ओके, तो जब हमने एक्स्ट्रा मैग्नेटिक फील्ड अप्लाई किया तो जो आपका प्लस हाफ है वो उसी के डायरेक्शन में अलाइन कर गया और माइनस हाफ अपोज कर गया. सो हियर द एमिटेड रेडियो फ्रीक्वेंसी इज डायरेक्टली प्रोपोर्शनल to the strength of applied field, and it is denoted by V is equal to Y B is naught upon 2 pi. So here the B naught is the external magnetic field experienced by proton. It is in the Gauss unit, and here the this one is denoted by the, we can say that is the gamma, or it is also we can say Y is here. That is the magneto-coherent ratio, that is between the nuclear magnetic moment and the angular moment. Okay, so that this gamma is equal to 2 pi mu upon hi, where the mu is equal to the magnetic moment of spinning nucleus, and the I is the spin quantum number. Okay, so it is the principle of the NMR, and or that is the, we can say that is the absorption of radiation by the nucleus in the magnetic field here. And here when I want to talk to about something like the precision frequency or the luminous frequency, the luminous frequency or the precision frequency is a frequency of precision that is identical to transition frequency. It is equal to the number of revolution per second made by the magnetic moment vector of the nucleus around the external field. Okay, so that this is the precision value. So here, now come to the next point, that is the interpretation of the proton NMR spectra. So the recorded NMR of the substance give the following information. So these informations about these are the, firstly the number of signal, then the position of signal, then the relative intensity of signal, then the splitting of signal. So here in this point, sir, we are discussing that the in the number of signal that indicates how many different kinds of proton are present. Okay, so there are we want to know that that it indicates that the how many different kinds of protons are present. In the second point, that is the position of signal. Here it indicates something about magnetic environment of proton. Magnetic environment of proton, and it is also known as the chemical shift. Okay. Then the third is the relative intensity of the signal. Here we know about that is a proportional to number of protons present. And in the fourth, that is the splitting of signal. And here we are talking about the spin-spin coupling. So it indicates the number of nearby nuclei, usually the protons. So these points we are discussing we are discussing in our next lecture. And this is a very important point. And here the some short definitions are also present, and those definitions are very important. Just like the we know we are talking, we will talking about the chemical shift. There is a one important point, that is the shielding effect, deshielding effect, spin-spin coupling. So these are very important topic which is related to the NMR spectroscopy, and these topic we are going to discuss in our next lecture. Okay, let's continue for second lecture of NMR spectroscopy. Now I want to complete my lecture for today, and now I stop my lecture. And if you have any doubt, so then query me, contact me.